What's good, everyone, and welcome back to another video. Today's topic is going to be on BST, binary search tree, and after this video, I'm going to be doing some LeetCode problems, and yeah, unless, I got bored of LeetCode problems, and I'm like, okay, let's just do a new topic, moving forward and stuff like that. But after this, I'll probably post like a little bit more of LeetCode problems and stuff like that. Anyway, so BST, binary search tree. Let me just write it out first. Okay, so what is a BST? It's just a binary tree with an extra rule about how values are basically arranged. So let's say for every node in with values, and we can just call it val or v. It's up to you guys. There's two rules. All nodes in the left subtree have value less than val. And then the right subtree, or all the nodes in the right subtree have values more than val. So values more than val. Okay? And so if I want to, let's say I want to draw it out, right? I'm going to have, let's say 8 here, and then we give it 3 here. Oh, I need to draw my 8 better. 3 here, let's say like 10, 1, 6, give it a set 4, and then 7, then like a 14 here, and let's say like 13 here. Okay, so it doesn't look very good, but I'm gonna actually expand it a little bit. Draw these lines. These lines just points to null, by the way, but sometimes you don't have to draw it. I'll draw it just because why not? Looks a little bit better anyway, I guess. It looks good enough. Okay, so when we check the rule for node 8, right, which is on the root, you see how like the 3, 1, 6, 4, 7, they're all less than 8, and then like the 10, 14, 13, they're all greater than 8, right? And then say when we check node for like node 3, then on the left side, 1 is less than 3, 6, 4, 7 are greater than 3, and so on. So that makes that ordering rule is what makes the BST. All right, so why is BST useful? Think of it as like BST being like the mix of sorted array in a tree, right? So like a sorted array, you can search very quickly, and then like a tree, you can insert and delete without having to shift tons of element. So in ideal case, which means that the tree is balanced, right? So tree is balanced. I'm trying to squeeze the word. Okay, well, that's clearly not how you do it. Tree is balanced. There we go. So ideal case, tree is balanced, then search, insert, delete are all going to be big O of log n. When we compare it, let's say we're going to do a comparison, right, with a normal array. So we have the unsorted array, a sorted array, and BST. By the way, it's going to be balanced. So for unsorted array, when we search, it's big O of n for search. However, for insert, it would be big O of 1. But But it's at the end. So big O of 1 at n. Sorted array, when we search, it's big O of log n. However, I'm just going to write big O of log n because we have search right here and insert right here. Big O of log n. However, when we want to do insert for sorted array, right, then it will become big O of n because we have to shift all the element. We have to do a lot of shifting. Now, obviously, for unsorted, you can kind of see that the insert is good, and then for sorted, the search is good. But BST makes it where all the search, insert, and delete all to be big O of log n, making it basically just a lot better compared to these two. So that's why BST is pretty good. And just keep in mind, there is a little catch. BST can become big O of n if the BST becomes skewed, meaning it's gonna look like a linked list. If it looks like a linked list, meaning something like this, then yes, it will degrade down to big O of n instead of big O of log n. So there's that. Anyway, let me just quickly erase this real quick. And then we're going to do some examples with like how the search works for BST. So I'm just going to quickly erase this. Okay, easy. All right, so search in BST. So it goes basically like the rule. You have a target, and I'll set a target in a bit. And then you have a current, and I'll set that in a bit as well. Well, for now, we're going to set it as A because we're just going to set it as A since it's the root. If the target, so T is less than C, which is the current, go left. And then if T is greater than C, then go right. T being equal to C, then found. You found it. So when we do it, let's say the target is 7. So target is less than 8. 7 is less than 8, so we go to the left. 7 is greater than 3, so we go to the right. 7 is greater than 6, so we go to the right again. And 7 equals 7, so we found, which is right here. And it's very simple, right? So this is literally like binary search on an array, but instead of indices, you follow left and right pointers. Let me erase it. Okay, let's say, what if like you're trying to search for something that's not in the tree, say 5. Again, you follow the same thing. 5 is less than 8, so we go to the right. Go to the left. 5 is greater than 3, so we go to the right. 5 is less than 6, so we go to the left. And then for 4, 5 is greater than 4, so we go to the right. However, 4 is the leaf, meaning it's going to point to null no matter it's left or right. So when that happens, you stop and print out that 5 is not found. Like that. So, and keep in mind, every step cuts the search space roughly in half if the tree is balanced. So that's why search is like big O of log n in the good case. So let me erase this real quick. There we go. Now, what about insert, right? So let's do insert now. There we go. Erase this real quick. Well, actually, now let's keep this. Yeah. Okay, so, because it sort of like follows the same thing again. But this time, instead of calling it target, we're going to call it val for value. me change it up real quick. Oh, actually, I don't need this. Oops, there we go. All right, so, and let me change up this part a little bit too. All right, so to insert val, you want to first check if the tree empty or not. If it is, the new node becomes the root. So let's say you have an empty tree and you want to insert 5. Then the 5 becomes the root. Now, other than that, let's say I want to insert 5 here. Then how exactly do I do it? Again, I followed the rule that I basically written out and just edit it into val in current.val. So we look at so let's say I want to insert 5 in here, right? We start at 8, which is going to be the current. Now the val is going to be less than 8, which is the current, so we go to the left. Now the current becomes 3. So is 5 greater than 3? It is, so we go to the right. Now the current is going to be at 6. Now 5 is less than 6, so we go to the left. Now it's going to be at 4. And when we look at 4, it's going to, you want to compare it one more time. And 5 is greater than 4. And since 4 points at null, you want to change that null to have it become the new node instead. So you insert 5 here. So for 4, the left of 4 will be null, but then for the right there will be a 5. So you want to find a null spot to create the new node 5 as 4 dot right or something like that. So right child. There's that. So now the new tree just looks like this. Let me erase the arrow real quick. There we go. So now let's say if I want to search for the value 5, then you do the same thing and then you'll find 5 this time. So insert in a BST is basically search for where it should go, and then when you fall off the tree, meaning hitting null, you plug it in there. Now, one more thing before I basically end the video is in order traversal, which means sorted order. And I remember talking about it in my previous video about pre-order, in order, and post-order for the DFS. And in order traversal is going to be, let me write it out. In order, what was it? It was left, root, right. Like that. Comma. Ignore that. Okay. So, and let's just do an in order in our BST, right? So I'm gonna erase the 5 just to keep it slightly fat. Just to do it a little bit faster. Okay, so first things first, we wanna write out visit. All right, so okay, so we start at 8 and we want to go to the left, meaning 3, and we go to the left again, which is 1. Now, when we look at the 1 for left, and for left, it's a null, so skip it. Then we visit 1. Now we check the right. It's also null, meaning we skip it, so we go back. And now, since 1 is gone, we look at 3. 3 root, so we visit 3. And then now we look at the right side of 3, which is 6. Now we look at the left side of 6, because now this is in order. So when we look at that, we want to reset and follow this left for 6. So now we have 4. Look at the left 4. Left 4 has nothing. It's null, meaning now we do the root, which means we visit 4. Then we check the right for 4. Again, that points at null, so we skip it and then we go back. So now 4 is gone. We look at 6. We finish the DFS for 6 on the left side. So now we visit the 6 and then move to the right, which is 7. 7 left is null, so we visit 7. And then 7 right is also null, so we finish 7. And now we go back to 6, which we just finished 6 as well. So we go back to 3. And once again, we already visited 3. And now for the 3 right DFS, we completed all of them. So we go back to 8. So now we visit 8 before moving on to 8 right. So 8 right will be 10. Now 10 left is null. So we skip it and then look at root, 10 root, meaning we visit 10 before moving on to 10 right. So we plug in 14. Now again, 14 left is going to be 13. 13 left. Now we do the 13 part. 13 left is null. Skip it. You visit 13. And then 13 right is null. So you skip it. So once you finish that, you go back to 14. You insert the 14 and look at 14 right. And it's a null. So you skip it. You finish 10. And then you finish 8. So this would be in order that you visited. And look, it's in order. 1, 3, 4, 6, 5, 7, 8, 10, 13, 14. It's all in order. Isn't that nice? So for any valid BST, in order traversal for the left, root, right always visits the node in increasing order. This is a fundamental property and gets used in like a ton of problems, like legal problems and stuff. So, as long as you do this and the result that you get is that you visit the nodes, the numbers, the values in order, and it's increasing sorted order, then there's nothing wrong. But if you do it and you get something like it isn't sorted, then something is wrong. So now let's just talk. Now, last thing before I end the video is the complexity. So I'm just going to point out like the good case and the bad case. And we're going to have n to be the number of nodes. So balanced BST. If the tree is balanced, then its height is h. If the tree is balanced, then its height is about log base 2n, like that, or just log n. So the search would be big O of h, which if it's big O of h, you just rewrite it so that it becomes big O of log n, like that. Just kind of insert it. You see how I just insert the O on both sides? Yeah, that's basically it. Same thing so that's for search, same thing for insert, same thing for delete. Now the space complexity will be big O of n because you are storing it big O of n to store all nodes. Let's say, for example, if we looked at a skewed BST, right? If you insert values in the sorted array into a simple BST that isn't balanced, then example, let's say like, oh god, I don't have space. Okay, I'm just gonna write it like this. Let's say like that. Like you want to just insert this into actually, sorry, I'm gonna write it like this. Let's say you want to insert these numbers into an empty BST, then you're gonna get a right skewed tree. So this is basically a linked list, meaning the height is gonna be h for -1, and then the search, insert, and delete becomes big O of n, and that's the worst case. So a basic BST is not guaranteed to be balanced. If you insert a sorted data, it can degrade to a linked list. So that's why we have advanced trees like the AVL, red-black trees that enforce balances. So for now, we don't have to dive deep into them yet, but this is basically the worst case versus the best case. So there's that. Anyway, that is basically it. Thanks for watching. See you guys next time.